predicted that it's this exchange of messenger particles that creates what we feel as force.
Experiments confirm these predictions with the discovery of the messenger particles for electromagnetism, the strong force, and the weak force.
And using these newly discovered particles, scientists were closing in on Einstein's dream of unifying the forces. Particle physicists reasoned that if we rewind the cosmic film to the moments just after the Big Bang, some 14 billion years ago, when the universe was trillions of degrees hotter, the messenger particles for electromagnetism and the weak force would have been indistinguishable. Just as cubes of ice melt into water in the hot sun, experiments show that as we rewind to the extremely hot conditions of the Big Bang, the weak and electromagnetic forces meld together and unite into a single force called the electroweak. And physicists believe that if you roll the cosmic film back even further, the electroweak would unite with the strong force in one grand superforce. Although that has yet to be proven, quantum mechanics was able to explain how three of the forces operate on the subatomic level.
And all of a sudden, we had a consistent theory of elementary particle physics, which allows us to describe all of the interactions, weak, strong, and electromagnetic, in the same language. It all made sense, and it's all in the textbooks.
Everything was converging toward a simple picture of the known particles and forces, a picture which eventually became known as the Standard Model. I think I gave it that name.
Professor Sheldon Glashow, Abdus Salam, and Steven Weinberg.
The inventors of the Standard Model, both the name and the theory, were the toasts of the scientific community, receiving Nobel Prize after Nobel Prize. But behind the fanfare was a glaring omission. Although the Standard Model explained three of the forces that rule the world of the very small, it did not include the most familiar force: gravity. Overshadowed by the Standard Model, string theory became a backwater of physics.
Most people in our community lost completely interest in string theory. They said, okay, that was a very nice, elegant thing, but had nothing to do with nature.
It's not taken seriously by much of the community, but the early pioneers of string theory are convinced that they can smell reality and continue to pursue the idea.
But the more these diehards delved into string theory, the more problems they found.
Early string theory had a number of problems. One was that it predicted a particle which we know is unphysical. It's what's called a tachyon, a particle that travels faster than light.
There was this discovery that the theory requires 10 dimensions, which is very disturbing, of course, since it's obvious that that's more than there are.
It had the massless particle, which was not seen in experiments.
So these theories didn't seem to make sense.
This seemed crazy to people.
Basically, string theory was not getting off the ground.
People threw up their hands and said, this can't be right.
By 1973, only a few young physicists were still wrestling with the obscure equations of string theory. One was John Schwartz, who was busy tackling string theory's numerous problems. Among them, a mysterious massless particle predicted by the theory, but never seen in nature, and an assortment of anomalies or mathematical inconsistencies.
We spent a long time trying to fiddle with the theory. We tried all sorts of ways of making the dimension before, getting rid of these massless particles and the tachyons and so on. But it was always ugly and unconvincing.
For 4 years, Schwartz tried to tame the unruly equations of string theory, changing, adjusting, combining and recombining them in different ways. But nothing worked. On the verge of abandoning string theory, Schwartz had a brainstorm. Perhaps his equations were describing gravity, but that meant reconsidering the size of these tiny strands of energy.
We weren't thinking about gravity up till that point. But as soon as we suggested that maybe we should be dealing with a theory of gravity, we had to radically change our view of how big these strings were.
By supposing that strings were 100 billion times smaller than an atom, one of the theory's vices became a virtue. The mysterious particle John Schwartz had been trying to get rid of now appeared to be a graviton, the long sought-after particle believed to transmit gravity at the quantum level. String theory had produced the piece of the puzzle missing from the standard model. Schwartz submitted for publication his groundbreaking new theory describing how gravity works in the subatomic world.
It seemed very obvious to us that it was right, but there was really no reaction in the community whatsoever.
Once again, string theory fell on deaf ears. But Schwartz would not be deterred. He had glimpsed the Holy Grail. If strings described gravity at the quantum level, they must be the key to unifying the four forces. He was joined in this quest by one of the only other scientists willing to risk his career on strings, Michael Green.
In a sense, I think we had a quiet confidence that string theory was obviously correct, and it didn't matter much if people didn't see it at that point. They would see it down the line.
But for Green's confidence to pay off, he and Schwartz would have to confront the fact that in the early 1980s, string theory still had fatal flaws in the math, known as anomalies. An anomaly is just what it sounds like. It's something that's strange or out of place, something that doesn't belong. Now, this kind of anomaly is just weird. But mathematical anomalies can spell doom for a theory of physics. They're a little complicated, so here's a simple example. Let's say we have a theory in which these two equations describe one physical property of our universe. Now, if I solve this equation over here and I find x equals 1, and if I solve this equation over here and find x equals 2, I know my theory has anomalies because there should only be one value for x.
Unless I can revise my equations to get the same value for x on both sides, the theory is dead.
In the early 1980s, string theory was riddled with mathematical anomalies kind of like these, although the equations were much more complex. The future of the theory depended on ridding the equations of these fatal inconsistencies.
After Schwartz and Green battled the anomalies in string theory for 5 years, their work culminated late one night in the summer of 1984.
It was widely believed that these theories must be inconsistent because of anomalies. Well, for no really good reason, I just felt that had to be wrong, because I felt string theory's got to be right, therefore there can't be anomalies. So we decided we got to calculate these things.
Amazingly, it all boiled down to a single calculation. On one side of the blackboard, they got 496. And if they got the matching number on the other side,